Okay, so we're starting off with Isaac Newton. Some of his biggest accomplishments were in calculus and physics. So he has three unpublished papers on calculus. He made advances in power series as well as Pascal's triangle. And he also worked with something called fluxions, which are essentially derivatives today. And he also calculated the modern partial derivatives. He had a little bit different notation, but this is essentially what he came up with. And we also have what's very common today when we talk about physics classes is the three laws of motion, Newton's three laws. Okay. We have Leibniz. He looked at calculus from sequences of differences, and we can see this up here at the beginning part. He also came up with the product rule, quotient rule, and chain rule, which you see in all your Calc 1 classes. We see here, here's the product rule, the second times derivative of the first, plus first times derivative of the second. He also worked with derivative of logs and derived the power series of differential equations. And his work was a little bit easier to extend and work with than some of his predecessors. We see a picture of him down here. Okay, moving on to differential equations. We have the Brachistone problem. This examined the fastest way to get from point A to point B, and most people would look at this and think, oh, it's the line, but this isn't necessarily the case, and sometimes it's not always the shortest route. It depends on how you're accelerating down there, and it's just a little bit different to look at. We also have Euler. He expanded differential equations to include trig functions. He also came up with the interchangeability theorem. You see this right here. And he also used multiple integration to find volumes, as well as advance the concept of functions for later generations. Okay, moving on to calculus. We have the early British text, A Treatise of Functions by Charles Hayes. Here he discovered that the area under the logarithmic curve between two x's is proportional to the difference between the corresponding y's. We also have that he studied the function y equals 80x, or the log of it. We also have Thomas Simpson, who did the New Treatise of Fluxions, 1737. This included several problems of max and mins and used the idea of partial derivatives. Okay. We have Colin Maclaurin, who came up with the Maclaurin series. We also have Euler, who defined exponential functions y equals a to the z. He makes the z the logarithm with y the base of a and developed a power series for any base a. Okay, moving on, we have here that he used the power series to find derivative of element of x. Okay, George Berkeley, he was criticized at the time. He often for setting values equal to 0 when it's not actually the case, and this led to the development of limits. We have Maclaurin, who would use limits, and we also have D'Alembert, who stated that dy dx is a limit of ratios as quantities approach 0. Okay, we also have Joseph Lagrange. He got rid of infinitesimals and limits and used series expansion, which we can see down here as a result for this. And the only problem with his work is that he assumed all differentiable functions have power series, but this is not always true. Okay, moving on to probability and statistics of the 18th century. We have, in the past, we have that Pascal assumed that each player is equally likely to win, but this is not always the case, which led to Bernoulli, who came up with estimating probabilities based on observed results. Okay, we have here that n choose r to the modern combinatorial n choose r times p to the r times q to the n minus r. We also have the doctrine of chances, which is how many trials give 50% chance. And this really only works if we have several failures per success. We see here a formula for it. And you could solve this using Taylor series. He is able to find a normal approximation to the binomial. And a picture here, we have Bayes' theorem, probability of A given B. And if we simplify this down, we get the probability of B given A times the probability of A over the probability of B. Okay, algebra and number theory. We have Maclaurin, who considered 2x2 system of linear equations, ax plus b equals c, dx plus ey equals f, and ended up with Cramer's rule without the determinants. We also have Cramer's paradox, which is the curve of order n determined by n times n plus 3 over 2. And you see here Lagrange popping up again with work with polynomials of the cube root. And you end up with 6 complex values for y, and thought of it as a use of permutations. We also have Euler's algebra. He looked at the number of integers prime to n and less than n. And he also worked with something called residues. And these are basically remainders. And we also have, during this time, Pell's equation, which we can see up here. Okay, non-Euclidean geometry. Sakurai came up with quadrilateral with 3 possibilities. Either they are both right angles, they are both acute, or they're both obtuse. And he used contradiction proofs, which ends up being a little messy when he tries to prove this. We also have John Lambert. He looked at the sum of angle related to the area and found that the defect is equal to 180 minus the sum of the angles. Okay, Euler in the bridge problem. We have 7 bridges, connect 4 places. He wanted a walk that crosses each bridge once. And you end up with 2 nodes that have odd degree. Then there is no path. And this actually, you have a picture of it down here. And this idea led to the field of topology, which is the maps and contours. We also have a woman mathematician here, Sophie Germain, who made progress on Fermat's last theorem. We also have Gauss, who worked with linear congruencies and did matrix-style computations. In the 19th century, we have now the modern concepts of limits defined. And we also have Bernard and Riemann, who developed criteria for integrable functions. And we have the development of least squares regression. And finally, we end with computer led to birth of linear programming.